Good morning, everyone. This is Siri Chandra from CSCF, roll number 24951A05BN, from Institute of Aeronautical Engineering. Subject is Probability and Statistics. Course code is AHS D11. Now my topic is Bayesian inference and Bayesian updating. Understanding how we learn from data. What is Bayesian inference? Bayesian inference is a powerful statistical method that leverages Bayes' theorem to update the probability of a hypothesis as new evidence comes to light. It's not so. This is a Bayesian theorem, which we got from Bayes' theorem. Bayesian inference is nothing which we adapt from Bayes' theorem to update the probability of a hypothesis as new evidence which comes to the light. It's not just about crunching numbers, it's about dynamically revising our beliefs, reflecting how confident we are in a proposition given observed data. So this just tells about our confidence in our given data. A statistical method using Bayes' theorem to update the probability of a hypothesis as new evidence arrives. So this is updated from Bayes' theorem, which is the update of the probability of hypothesis, which is used as new evidence arrives, where new evidence arrives. It enables us to revise beliefs dynamically, reflecting how confident we are in given observed data. This revises our beliefs dynamically, which reflects in our given data, observed data. It is used in science, engineering, medicine, and decision making. This is also used in decision making, which is very crucial. Bayes' theorem, the heart of Bayesian inference. At the core of Bayesian inference lies Bayes' theorem, a mathematical formula that quantifies how new evidence changes our beliefs in hypothesis. This P of H by E is equal to P of E by H into P of H by P of E is our formula for Bayes' theorem. So we'll learn about separate components separately. So P of H means prior probability for our initial belief about the hypothesis before seeing any evidence. So this is before seeing any evidence, this is our value. P of E by H, likelihood for how probable the evidence is if the hypothesis is true. If the hypothesis is true, that is our value. P of H by E, posterior probability for our updated belief about the hypothesis after considering the evidence. Next is P of E, marginal likelihood for the overall probability of observing the evidence, serving as a normalizing constant. Next is initiative example. Which ball did the cookie come from? So imagine you have two balls of cookies. Ball 1 of 10 chocolate chip and 30 plain cookies. Ball 2 of 20 chocolate chips and 20 plain cookies. You pick a cookie at random and it's plain. What's the probability it came from bowl 1? Using Bayes' theorem, we can find out initial belief. Example, 50% chance from each ball based on the observation of a plain cookie and the known cookie compositions of each ball. This simple scenario perfectly illustrates how we update our beliefs with our data. The role of prior and likelihoods. This prior and likelihoods are the role that plays a crucial role in this topic, in this concept or whatever it is. So priors, initial beliefs. Priors encapsulate our initial knowledge, our beliefs about the hypothesis. This priors encapsulates our belief and knowledge about this hypothesis. They can be informed by past experiments, expert opinion, or even a uniform distribution if no prior information, if there is no prior information available. They can also be informed by past experiments, like the past things past which have happened, or the expert opinion, or even a even distribution, or opinion of expert, or past experiment experiences. Next is likelihood. Data support. Likelihood measures how well the observed data supports each competing hypothesis. It's the probability of seeing this data. So this is the probability of seeing its data. Next is posterior, refined understanding. The posterior probability is the result of combining the prior and the likelihood. It represents R about the hypothesis after incorporating the new evidence. The choice of prior can significantly influence the posterior, especially with limited data. Next is Bayesian updating, learning step by step. One of the most elegant aspects of Bayesian interference is its iterative nature, known as Bayesian updating. It allows us to continuously refine our understanding as new information becomes available. Iterative refinement. When faced with multiple pieces of evidence, Bayesian updating allows us to incorporate them sequentially. The posterior probability obtained after considering this became the new prior for evaluating, and so on. Next is continuous learning. Each subsequent update refines the probability of our hypothesis. This process mirrors how we learn in real life, constantly adjusting our beliefs as we gather more information. For instance, if you are trying to determine if a die is loaded, each roll provides new evidence to refine your beliefs about its fairness. Increased certainty. As more data is observed and incorporated, the posterior distribution tends to become uh, tighter and more concentrated, reflecting increased certainty in the hypothesis supported by the evidence. Bayesian versus frequentist perspectives. Understanding the differences between Bayesian and frequentist approaches key to approaching the unique strength of Bayesian inference. Frequentist view, Bayesian view. Um, Parameters are fixed but unknown. They have one true value. Data is random. Hypothetical repetitions of an experiment would yield different data sets. Focus on p values and confidence intervals, which describe the long run frequency of obtaining similar results under repeated sampling. Bayesian view. Uh, Parameters are random variables with probability distributions representing an uncertainty about their values. Data is fixed and observed. We condition our beliefs on this observed data. It provides credible interval which directly express the probability that a parameter's true value falls within a given range. Visualizing Bayesian updating. Coin toss example. Consider a simple coin toss. We start with a prior belief about the coin's fairness. Perhaps that it has a 50% chance of landing heads. As we observe the heads and tails, we update our posterior distribution for the cons bias. Initially, our posterior might be wide, reflecting high uncertainty. With more data, more tosses, the posterior distribution tightens, becoming more concentrated around the true bias of the coin. This visualization clearly shows how our certainty increases with incoming evidence, with incredible intervals narrowing to pinpoint the likely true bias. Real world applications of Bayesian inference. Bayesian inference is not just theoretical power, critical system, and also this. It is used in medical diagnosis, machine learning, finance, and robots. Why Bayesian thinking matters? The Bayesian approach forces you to be honest about your prior beliefs and how new data shapes them. So it learns about principal learning, explicit uncertainty, smarter choices, and continuous application. Thank you.